Hi, I'm Michaela. I'm going to be doing my Unit 4 case connection video presentation. Here's this. All right, so I chose to do case study 1. Case study 1 is about a newborn girl who appeared normal at birth, but then within 24 hours she developed lethargy, hypothermia, and apnea. The attending physician suspects a metabolic disorder. So her lab showed an ammonia level at 314 and then quickly rose to 600. Her urine also showed uric acid levels were markedly elevated, and her citrulline level was normal. But you can see the range is 12 to 55, so it is on the low end of normal. So that's kind of what I went with for my case study. So first, the case study wanted to discuss the normal mechanisms of ammonia transfer. So first, in the upper right picture with the liver and the muscle, you can see the alanine is coming out of the muscle from protein catabolism and going to the liver. In the liver, we can do transamination reactions by AST and ALT to help move the nitrogen group off of the amino acid and onto a keto acid. This requires pyridyl phosphate to do this as a cofactor. So the far left is a picture of a transamination reaction, kind of turning an amino acid into a keto acid and then alpha-ketoglutarate into glutamine or glutamate. This other picture, I have an example with the names of alanine going into pyruvate and then alpha-ketoglutarate going into glutamate. So next, glutamate, which was produced from the transamination reaction, will be deaminated. This requires NADP plus and uses the enzyme glutamate dehydrogenase. This will end up releasing some free ammonia. This reaction is reversible, so we'll see that come into play a little bit later on with the fasted state implementation of the nitrogen transport system. All right, so from glutamate that we had in the previous slide, we can turn it into glutamine by glutamine synthase. So essentially combining the ammonia with glutamate can make glutamine. This is important because glutamine is a non-toxic carrier of ammonia, so it's able to move around the system without bad effects. In the liver, once the glutamine gets there, it can go under a reverse reaction by glutaminase and go back into glutamate. This releases ammonia for the urea cycle to use in the liver. So the connection of nitrogen transport to the fasted state. So I talked about this before, about how glutamate can turn into alpha-ketoglutarate by glutamate dehydrogenase. So we can repackage the ammonia with the alpha-ketoglutarate and turn it back into glutamate, or vice versa. So it all depends. When we're unpackaging glutamine back into glutamate, we can use that glutamate and put it back through this reaction and turn it into alpha-ketoglutarate, which can then go into the TCA cycle. So it's can be used as a substrate. In addition, this bottom equation that we've seen prior also, this is the glucose-alanine cycle, that pyruvate that's created as part of this, transition of the nitrogen group can also be used as a substrate for gluconeogenesis. So they're kind of connected as far as moving nitrogen around and then having substrates for glucose production in the fasted state. So in this case, we found out that the orotate levels were elevated, and then there was a low to normal citrulline level. So if we look at this picture, which I'm hoping my face is not in front of, I put arrows by kind of the levels of each thing. So the carbamoyl phosphate is going to be elevated here. And that is because I'm assuming the most likely situation for the enzyme deficiency is the ornithine transcarbamylase, or the OTC deficiency. So that is kind of highlighted in the middle here as well. If that enzyme's not working, we'll get a backup of the carbamoyl phosphate. And this will cause it to shuttle out of the mitochondria and go into a different pathway, which will cause increased orotate levels to occur. And this will go through, instead of the carbamoyl phosphate 1 enzyme, it will go through the second one, which is used in the pyrimidine synthesis pathway. So that's where we get the extra orotate levels, and that kind of gives us a hint of like where the enzymes are a little off balanced. You can see also here citrulline levels are a little low. They were 10 when the normal is like 12. Anyway, so that gives us a sign that this enzyme might be deficient in not producing enough citrulline. And then since this is low all the way throughout the cycle, we can see low levels of arginine and arginase, which arginase is responsible for cleaving urea out of this cycle, and so it would make sense why we have a high serum ammonia level, because this isn't happening as well. So the least likely deficiency in my mind would be arginase, and that's because the citrulline is like low to normal. And I was thinking that the arginase deficiency would be least likely because we still are seeing high serum ammonia levels, so therefore we're not splitting it up as well. Let's see, we already have ammonia packaged into arginine here. But it's interesting because research shows that for both the OTC deficiency and the arginase deficiency, that supplementation of arginine is actually one of the ways that we could help the urea cycle function better. Yes. Okay, so if it is an OTC deficiency like I was thinking, which amino acid becomes essential? So here it's going to be arginine, and this is kind of what I was talking about before with the supplementation being effective here. But essentially, the arginine was non-essential because through the urea cycle, our body was making the amino acid. But now, if we have an upstream issue, then we're not making the arginine. So then it would be required for our body to start taking that or supplementing it to be able to still effectively cleave urea. So then I also talked about in my paper that excess ammonia presence can cause cerebral edema, which is likely the case with the child. So hemodialysis to help filter out that excess ammonia, and then benzoate and phenylbutyrate can help bind to the excess nitrogen or the ammonia and help rid that of the body to help with the neurologic side effects of this one. All right, so then case study 3 is about a man who presents with severe pain in his great right toe. He's diagnosed with gout. His plasma urate levels are elevated and his urine uric acid levels are low. So there's a couple different ways that the case study wants to discuss this. So first, the possibility of how he has his gout. We're going to discuss decreased excretion of urate. So if this was the case, it's usually related to poor renal function. So we see that in like chronic kidney disease, poor GFR, creatinine clearance, that kind of thing. We also see occasionally that when people have acidotic states like lactic acidosis, that the body prefers to filter the lactic acid and that ends up building up the uric acid. That could be a case, probably less likely with this man knowing his dietary intake, but we'll get back to that. And then my research showed other disorders such as Down syndrome, and then acute states of hypovolemia and overdoses or medication ingestions can also lead to decreased excretion and therefore buildup of urate in the system. So next, I'm going to start talking about purine salvage, but first we need to talk about degradation. So inosine and guanine are purines, like part of the nitrogen-based nucleotide compound. So in this picture, you can see that they each kind of go down into their parts. So hypoxanthine and guanine, and then they go down into xanthine. And then xanthine has the enzyme xanthine oxidase, which decreases it down into uric acid. So that's where a lot of gout treatments are directed at, actually, because xanthine is more soluble than uric acid. Uric acid in excess is going to build up in the tissues and crystallize, like we're seeing in this guy. So it's possible that, obviously degradation is working well if we have high uric acid in this guy, but purine salvage could be part of his issue. So purine salvage, what we do is take the hypoxanthine and the guanine and turn them back into the nucleotide bases to prevent excess uric acid. So if this guy's not able to do this very well, then he will have increased uric acid. So the enzyme important here is the hypoxanthine guanine phosphorybosyltransferase, transferase, or HGPRT. So essentially this is going to help kind of convert backwards upstream to avoid more uric acid being created. But if this enzyme is not working, then the reaction is going to flow downstream and go towards xanthine and then therefore uric acid. And here you can see that the hypoxanthine and the guanine are combining with PRPP, which is the sugar, and then going back into their nucleotide base of IMP, GMP. So, this disorder would be called Lesch-Nyhan syndrome if this is the enzyme that this patient is having difficulties with. Next, overproduction of purines. This can happen a couple different ways. So you can have a deficiency of glucose 6-phosphatase enzyme, and this would be called von Gurke's disease. So essentially, glucose 6-phosphatase is the enzyme that helps release glucose free into the system from glucose 6-phosphate. So if that enzyme's not working, we're going to have excess glucose 6-phosphate. Since it can't go out into different systems, it's going to shuttle down through the pentose phosphate pathway. And that is going to end up giving us more ribose, 5-phosphate, and therefore increased PRPP, so the sugars, which will let us create more purines, and then we'll have an increase of uric acid. So, let's see. So that's one possibility, is having that deficiency in that enzyme. The other possibility is that this guy just drinks a ton of soda, which is filled with fructose, which eventually metabolizes to fructose 6-phosphate and then to glucose 6-phosphate. And then we end up kind of in the same boat here with shuttling a lot of that down into the pentose phosphate pathway and creating more and more purines. So for this guy, I would say the first plan of action would be to stop drinking so much soda and see if that helps the gout at all. If it doesn't, then you need to investigate further for the glucose 6-phosphatase or the HGPRT issues. In addition, research says that vitamin C supplementation can help bind to gout or help with absorption of uric acid and kind of rid that so it doesn't build up in peripheral tissues. And then we talked about allopurinol a little bit, how it acts on xanthine oxidase. Here's my references.